Good morning, everyone. Today we will be presenting this year's challenge for the Electronic Instrumentations and Optoelectronics course. I will begin by explaining the motivation behind the sensor choices, its operating principles, and the system-level implications of using a MEMS-based dual-frequency pressure sensing architecture. So, let's begin. First, we will begin with the context and motivation. The objective of this project is to measure pressure fluctuations generated under turbulent boundary layers, which are a key phenomenon in aeronautical flows. These measurements are relevant for both flight tests and wind tunnel tests, where accurate characterization of aerodynamic noise and flow behavior is required. The system must satisfy several strict requirements. First, it must operate over a wide bandwidth up to 100 kHz in order to capture both low-frequency flow structure and high-frequency turbulent components. Second, it must provide high sensitivity since the pressure variations can be very small. Finally, it must remain robust under extreme environmental conditions, typically found in aeronautical testing. Conventional microphones are not suitable for this application, mainly due to their limited bandwidth, sensitivity constraints, and lack of robustness in harsh environments. So, why MEMS? To address these limitations, MEMS technology is selected. MEMS sensors offer a very small physical size and low mass, which makes them ideal for integration into aerodynamic surface without disturbing the flow. In addition, they provide a significantly higher frequency response compared to traditional acoustic sensors. Another important advantage is their scalability, which allows the implementation of distributed sensor arrays for spatial resolved measurements. Finally, MEMS devices are mechanically robust and can operate reliably under temperature and pressure variations encountered in aeronautical testing environments. The key idea is that MEMS technology enables both high spatial resolution, broadband pressure sensing, which are essential for this application. So, the sensing principle is based on piezoelectric cantilevers made of ASCN material. The system uses two types of mechanically distinct structures. Large cantilevers are optimized for low-frequency operation. They are more compliant, meaning they deform more under pressure, which increases sensitivity but limits the resonance frequency. On the other hand, small cantilevers are stiffer and therefore respond to high-frequency components, but with lower sensitivity. This dual structure allows simultaneous sensing of low and high-frequency pressure fluctuations within a single integrated MEMS device. As shown in the figure, both geometries are integrated on the same platform, enabling compact and efficient broadband sensing. The frequency response of the system clearly shows the complementary behavior of the two channels. At low frequency, the low-frequency channel dominates due to its higher sensitivity. As the frequency increases, its response gradually decreases. In contrast, the high-frequency channel becomes dominant and extends the usable bandwidth up to 100 kHz. The overlap between both responses is particularly important since it ensures continuous spectral coverage without gaps. Additionally, resonance peaks appear due to mechanical nature of the cantilevers. These resonance defines the effective operating limits of each sensing limit and confirm the physical validity of the design. At system level, the sensor behaves as a high-impedance RC network due to the piezoelectric nature. This has direct consequences for the analog front-end design since it requires a high input impedance and amplification to avoid signal attenuation. The system also exhibits a very wide dynamic range. At around 120 dB SPL, the output signal is in the order of 200 millivolts. However, at extreme conditions such as 175 dB SPL, the output can exceed 10 volts, which introduces a risk of saturation if the system is not properly designed. In addition, the system must operate under strict environmental constraints. Flight tests require operation down to minus 65 degrees Celsius, while wind tunnel tests can reach up to 70 degrees Celsius. These conditions affect both the sensor and the electronics and must be taken into account in the design. This block diagram shows how the sensor integrates in the full system. The MEMS sensor converts pressure into an electric signal. The signal is then conditioned by the analog front end. After that, it is digitized and processed by the data acquisition system. The important point is that the sensor characteristics directly influence all the subsequent stages. To conclude this part, the MEMS dual frequency architecture provides a physical consistent solution that combines both sensitivity and bandwidth in a single device. It is fully compatible with the required aeronautical environment conditions and forms a solid foundation for the subsequent stages of the system design, particularly the analog signal conditioning and data acquisition chain. The next step in the project focuses on the implementation of application stages and full integration system. Now I will briefly discuss the signal conditioning stage, which builds directly on the sensor characterization. To properly interface the sensor, we use a high-performance operational amplifier. In this case, The OPA828 JFET op amp is selected because it has extremely low input bias current, which minimizes loading on the high impedance sensors. It is also powered by a plus minus 5 volts, which naturally limits the output voltage and protects the ADC from the overvoltage conditions. This ensures both accuracy and robustness. The high-pass filter is implemented using a bias resistor and sensor capacitance. This removes DC components and defines the low-frequency cutoff. For the low-frequency channel, the cutoff is approximately 8 Hz. For the high-frequency channel, it is around 20 Hz. These values ensure that all relevant acoustic signals are preserved while unwanted low-frequency drift is removed. On this slide, we present the non-inverting amplifier stage used to scale the sensor signals before digitization. The main goal here is to match the sensor output to the ADC dynamic range while avoiding the need for complex automatic gain control. For the low frequency path, we use a gain of 10. This is implemented using a feedback network with a 9 kilo ohm resistor and a 1 kilo ohm resistor. For the high frequency path, the gain is increased to 20. This compensates for the lower sensitivity of the high frequency cantilevers, ensuring that both channels produce comparable output levels. Looking at the amplifier characteristics, we can see that the OPA828 is well suited for this application. It has an extremely low input bias current on the order of picoamps, which is essential because the sensor itself has a very high output impedance. It also has low voltage noise, which helps maintain a high signal-to-noise ratio. In addition, the high gain bandwidth product ensures that the amplifier can operate correctly over the required frequency range, up to 100 kHz. Overall, this stage provides stable, low-noise amplification while preserving the integrity of the sensor signal. After amplification, the signal must be filtered before digitization to prevent aliasing. For this purpose, we use a second-order cell-and-key low-pass filter with a Butterworth response, which provides a flat passband and no ripple. The filter is implemented using the OPA1642 dual operational amplifier, which allows us to save PCB space and also acts as an ADC driver thanks to its high slow rate. The design uses an equal component configuration with capacitors fixed at 1 nanofarad. For the low frequency path, we set the cutoff frequency to 15 kHz. This results in a resistor value of approximately 10.5 kilo ohms. For the high frequency path, the cutoff is set to 150 kHz, corresponding to a resistor value of about 1.05 kilo ohms. These cutoff frequencies are chosen to match the bandwidth of each channel while ensuring that higher frequency components do not fall back into the signal band during sampling. Finally, the system targets a sampling rate of 2 megasamples per second, which provides sufficient margin to prevent aliasing and ensure accurate digital representation of the signal.
To start with the signal integrity, let's look at the signal levels at the ADC input. We established a reference level of 120 dB SPL, which is the standard for these aeronautical tests. For the low frequency path, our sensor gives 10 millivolts per Pascal, which results in 0.2 volts. After applying a gain of 10, we send a clear 2 volts RMS signal to the ADC. On the other hand, for the high frequency path, the sensor is half as sensitive, so we compensate by doubling the gain to 20. This way, both signals reach the ADC at 2 volts, making the most of the dynamic range without saturating the system. Now, let's talk about the noise floor. We calculated the noise by adding the contributions of our amplifiers and filters. In the low frequency path, the total noise is only 4.94 microvolts. In the high frequency path, because the bandwidth is 10 times wider, the noise naturally goes up to 31 microvolts. In short, our analog circuit is very quiet and stays well above the 90 dB requirement, ensuring the electronics won't interfere with the acoustic measurements. Let's continue with the per-channel digitization. The most important decision in our architecture was moving away from traditional multiplexing. Usually, many sensors share one converter, but this creates timing delays and interference, which is a disaster for beamforming. Beamforming needs all sensors to be perfectly synchronized to calculate where the sound is coming from. By using edge digitization, we give each sensor its own dedicated ADC. This allows simultaneous sampling across all 160 channels. Also, since we convert the signal to digital right at the source, the data is protected from any electrical noise while traveling through the 5-meter cable. Regarding the ADC selection, we chose SAR technology over the more common sigma delta. Why? Because sigma delta converters use internal filters that create create group delays, which could ruin our phase consistency. The SAR architecture provides a perfectly linear response and zero latency. It's the only choice that ensures the precise timing we need for high quality results. The specific chip we selected is the AD463024. It's a 24-bit dual channel converter that samples at 2 million samples per second. This gives us a huge margin for our 100 kHz target. Physically, it's incredibly thin, only 1.72 millimeters high. And this is key because our total limit for the whole system is 2 millimeters. Now we reach the most critical part of our noise analysis, the total system SNR. To determine the final performance, we must add the ADC's intrinsic noise, which is 17.7 microvolts RMS, to our analog front-end calculations. This value accounts for both the 24-bit quantization noise and the internal thermal noise of the AD4630 chip. For the low frequency path, the combined noise is approximately 18.38 microvolts. This results in a final system SNR of 100.7 dBs, giving us a comfortable 10 dB margin over the project requirements. Moving to the high frequency path, the wider 150 kHz bandwidth naturally integrates more noise, reaching 35.7 microvolts. Even so, the total SNR remains excellent at 94.9 dBs. The vital takeaway is that even in our worst case scenario, we are still 5 dBs over the strict 90 dB limit set by Clean Sky 2. This proves that our combination of high-end JFET amplifiers and the 24-bit SAR architecture was the right choice to ensure laboratory-grade precision in a flight environment.
Moving further down the digital chain, once our ADCs digitize the analog signal, we face an issue. The ADC's output data is in a serial format, but our downstream serializers require parallel inputs. To solve this, we have implemented a dedicated serial in parallel out shift register bank for each group of 8 sensors with their high frequency and low frequency simultaneously. Rather than complicating the system, this layer simply captures the serial lanes and packages them into perfectly synchronized parallel words, preparing them for the next stage. Something that we have taken deeply into account is for our acoustic beamforming to work properly. For that, phase coherence is absolutely critical. All 160 channels must be sampled at the same exact instant. We have achieved this using a distributed master clock routed through an H-tree topology, which guarantees that the signal travel time is identical across all ADCs. To maintain our high SNR, our jitter budget dictates that we stay below 8.3 picoseconds. Thanks to the ultra-low jitter of our chosen ADCs and the strict clock distribution, our system easily outperforms this requirement. Zooming out to the array level, we have 160 channels to manage. To handle this massive amount of data, we divided the array into 10 modular groups. Each group concentrates 16 channels into a single high-speed LVDS link running at 768 megabits per second. This gives us a highly synchronized continuous raw throughput of 7.68 gigabits per second for the entire array. To physically mount all of this into the aircraft, we use the flexible PCB, housing everything from the main sensors to the serializers. To preserve signal integrity in such a tight space, the physical separation between the micro-level analog inputs and the high-speed digital regions must be shielded completely with a continuous ground plane.
Moving on to power management, we need to generate 5 different clean voltages from a very noisy 28-volt aircraft battery. We have plus and minus 5 volts for the amplifiers, 5.4 volts for the ADC core, and lower voltages for the digital parts. To keep the SNR of the ADC, these voltages must be extremely pure. All these components are integrated directly on the flexible PCB. To do this without overheating the board, we use a two-stage strategy. If we converted 28 volts to 5 volts directly, the board would melt from the heat. So, in stage 1, we use a silent switcher that drops the voltage to 6 volts very efficiently. It's called silent because it doesn't create electromagnetic interference. In stage 2, we use ultra-low noise regulators, LDOs, that clean the remaining ripples, leaving only 0.8 microvolts of noise. This ensures the ADC reference is clear. To finish, we organized the array into 10 identical power blocks. Instead of having one big power supply in the middle, we distributed 60 small regulators across the 5-meter strip. This decentralized architecture is vital for two reasons. It prevents hotspots by spreading the heat across the aircraft skin, and it prevents voltage drops, ensuring every sensor gets perfect power regardless of its position in the array. This makes the system stable, reliable, and ready for flight.
Finally, to get the digital data of the PCB and into the remote DAQ, we use a 12-pair STP harness. This harness carries our 10 high-speed data links, our master clock, and the DC power by transmitting a robust digital LVDS signals over twisted pair instead of sending fragile low-level analog signals over long cables. We completely eliminate cable-induced noise and crosstalk, guaranteeing pristine 24-bit data integrity.
Now, I will explain the data acquisition, software processing, and validation strategy of the system. This slide shows the complete acquisition change, from the MEMS sensor to the host PC software. Its MEMS sensor provides two analog outputs, one low-frequency channel and one high-frequency channel. These signals first go through the analog front end, where we perform AC coupling, low-noise amplification, and anti-aliasing filtering. After that, the conditioned signals are digitized locally using dual-channel ADCs. This is one of the key decisions of the design. Instead of sending weak analog signals through long cables, we digitize them close to the sensors. Then, the digital data is grouped by serializers and transmitted through digital links to the remote DAC. On the DAC side, the serializers recover the streams, and the FPGA reconstructs the original synchronized channels. Finally, the host PC performs calibration, SPL calculation, spectrum analysis, and data storage. The selected DAC is not a conventional analog input DAC. It is a digital FPGA-based acquisition unit. The analog-to-digital conversion has already been done on the flexible PCB. Therefore, the remote DAC receives 10 digital streams. Each stream contains 16 already digitized channels. Since we have 10 streams, the FPGA reconstructs the full 160-channel array. The FPGA has several real-time tasks. First, it monitors the link status to check that each deserializer is correctly locked. Then, it performs frame alignment and channel reconstruction so that every sample is assigned to the correct MEMS sensor and to the correct LF or HIF path. It also adds timestamps, detects errors, buffers the data, and can optionally decimate the signals for long recordings. Finally, the reconstructed data is sent to the host PC using Ethernet. We are doing this since we want full rate acquisition. We require a high-speed Ethernet interface because the total data rate is very high. Once the data arrives at the PC, the software does not directly receive acoustic pressure. It receives raw ADC codes. The first step is to convert each ADC code into voltage. This conversion uses the ADC resolution and the full stage voltage of each channel. Then, we apply offset correction. This is important because each sensor, amplifier, and ADC channel may have a small DC offset. Therefore, the offset is measured during calibration and subtracted independently for every channel. After that, the corrected voltage is converted into pressure. This is done using the calibration coefficient Ki. This coefficient includes the sensor sensitivity, the analog gain, and the individual calibration of each channel. Finally, the software calculates the sound pressure level, or SPL, using the RMS pressure on the standard reference pressure of 20 micropascals. So, in summary, this software chain transforms raw digital samples into calibrated acoustic quantities. The software provides both time domain and frequency domain outputs. In the time domain, we obtain the pressure signals in pascals, the RMS pressure, and the SPL for each channel. In the frequency domain, the software calculates the FFT magnitude spectrum and the power spectral density. It also performs inconsistency checks between the LF and HF channels, especially in the overlap region. This helps detect calibration errors or abnormal channel behavior. The main channels here is storage. The complete system generates 7.68 gigabytes per second, which is equivalent to 960 megabytes per second. This means that the continuous full rate storage is only practical for short acquisitions or a very high performance storage system. For long tests, we need to reduce the amount of data. We can use decimation, channel selection, or trigger acquisition. The recommended formats are TDMS or HDF5 because they can store large binary datasets together with metadata. The validation strategy checks the complete gain from the MEMS sensor to the final acoustic data. First, we validate the electrical gain and offset. An on-input signal is injected and the reconstructed voltage is compared with the expected value. Then we validate the LF and HF bandwidth responses. This confirms that the filters and the two sensor paths behave correctly over their intended frequency ranges. We also verify the ADC scaling to make sure that the conversion from ADC code to voltage is correct. On the digital side, we test the link integrity, frame alignment, and channel order. This is essential because the FPGA must reconstruct the correct 160 channel map. Clock quality is also validated by checking jitter and skew, since timing errors would affect phase coherence and beamforming. Finally, we perform acoustic calibration and final SNR validation. The system is accepted only if the FPGA reconstructs all the 160 channels without missing frames, corrupted words, or channel swaps.
Moving on to the budget analysis, the total cost is around 15.27 thousand euros. The largest cost contribution comes from the digitalization stage, mainly the ADCs. This is expected because we need 24-bit precision and simultaneous coherent sampling for all channels. The second major cost contribution comes from the remote DIQ. This is required because the system must process 7.68 gigabits per second in real time and reconstruct 160 synchronized channels. The infrastructure cost, including flexible PCB and the cable harness, is also insignificant. However, it is essential because the system must fit within the 2 mm aerodynamic profile while transmitting robust digital data. Moving on to the final SNR compliance, according to the validation calculation, the low-frequency path achieves 100.7 dBs and the high-frequency path achieves 94.9 dBs. Therefore, both paths satisfy the requirement. The analog frontend has the strongest impact on the high-frequency path because the high-frequency channel uses higher bandwidth and higher gain, which increases the contribution to the thermal noise. For a low-frequency path, the ADC noise becomes dominant limitation because the analog noise is lower. The important part is that after digitalization, the digital chain does not degrade the analog SNR. The SIPO stage, serializer, cables, FPGA transmit digital information, so they are not affected by analog crosstalk or cable noise in the same way as an analog transmission system. Thermally, the system is self-regulating. Our 7-watt total load is low enough that at 70 degrees, the aircraft skin handles our cooling as a natural heatsink. Conversely, at negative 65, that same self-heating keeps our electronics from freezing. We achieve this by using low-power serializer, efficient switching regulators, and a decentralized layout with 10 zones to completely eliminate hotspots. We have also validated our physical and timing constraints. We maintain the strict sub-2 mm aerodynamic profile, and for phase coherence, the ADC architecture and the H-trig lock distribution guarantee sub-microsecond synchronization, completely avoiding the filter delays you would normally see with other ADC topologies. Of course, deploying these complex electronics on a flex PCB in an aerospace environment carries real-world risks. To mitigate moisture affecting our high-impedance analog nodes, we apply a conformal coating. To prevent vibration fatigue, we place rigid stiffeners under our components, and to ensure system reliability, we use clock buffers and redundant wiring to prevent single points of failure. As you can see in our compliance matrix, the design passes all target values. From bandwidth and dynamic range to thickness and temperature extremes, the architecture successfully meets all rigorous criteria of the Clean Sky 2 program. In conclusion, by replacing legacy analog multiplexing with local edge digitalization, we successfully capture 160 perfectly coherent channels from 80 MEMS sensors. The result is a high, robust, scalable platform ready for advanced aeroacoustic measurements. Thank you very much for your attention. We are open now for questions.